Greetings, Saints Man. This is lesson 8.1 regarding similar polygons. I'm going to start a new journey with regarding polygon similarity, and in particular, talk about similar quadrilaterals and what that means. So the first thing that we needed to go back and discuss is this notion of what a ratio is. So, plainly put, a ratio is when we have is expressed as a division of two quantities. But it's not division. Okay? So here are the ways that we see it symbolically expressed. We're going to see A to B, or also written as A colon B, also written as A to B, or written as A colon B, but read as A to B, and A over B. But gentlemen, this is not technically a percentage. Okay, so here's what I want you to consider. Let's take a ratio, right? So you get invited to a party, and you show up, and the ratio of male attendees to female attendees is 1 to 2, right? Male to female. Now, what does that mean? In other words, the question being, if we think about this as in terms of percentage, what percentage here are going to be men that are at this party? Now, when you see this 1 to 2, or even if it's expressed this way, it does not mean 50%, right? Okay? It doesn't mean 50%. 50% would be half of the attendees are male. That's not what it is. For every one man, there's 2 women, being that it would be really 1/3, right, of the attendees are male, or 33% are male, or 66.767 or 67% effectively are going to be female. So just another way to kind of think about how we're thinking of one to another, and how we express these ratios. We're going to think about this in terms of polygons. So what we wind up seeing is what we're going to call what winds up being proportionality, right? So let's go ahead and throw this guy out here, get a triangle, and it's going to look identical at first, but what we're going to wind up doing is drawing a larger one over here. Okay. What's great is that my drawing tool makes a perfectly proportional triangle, right? So for every for example, for every 1 inch it may expand one side, it's going to, or 1 millimeter, it's going to expand the other side proportionally. And here's what I mean. We're going to take this triangle A, B, C, and then we have J, K, and L. Okay? So here are the measurements. 21, 27, and 36 for the side lengths for ABC. And then we have 28, 36, and 48. Okay? So here's what this means. What we have here are similar polygons in that we have A, B, C, and we have this single squiggle. It's not like congruence where we have the single squiggle over the equal sign. It's a single squiggle, similar to JKL. So here's our similarity statement. Similar to congruence statements, right? In that these have corresponding parts. This little squiggle means similar. And what that means when we have something that is similar is that similar polygons are proportional, meaning that all the corresponding sides have a ratio and have the same ratio. And the corresponding angles don't have a ratio. They're all going to be the same. They're all going to be congruent. Here's what I mean. A corresponds, right, first letter, to J, which is the first letter, just like we dealt with congruent. So this would be pretty straightforward with you guys, right? Not a lot new to learn in this regard. B, what would B correspond to? Think about it. Of course, it's going to be the second letter, which is K, right? And these are going to be congruent angles, as well as C is going to be congruent to L. Now, think about this. If we have a scale factor here, right, we're going to set up this proportionality. The scale factor means that if I set up a proportion for each side that corresponds, for example, AB to JK, those guys will have the same scale factor if I create that that ratio for each of these sides, right? So correspondingly, right? So AB to JK, BC to KL, and then AC, first and third, right? To J, ooh, that's a fairly terrible C. AC to JL. All right, so let's take a look. This is one of these guys. Okay, so going back here. AC. All right, first and third. So that's the last one we just discussed with JL. First and third, right? So 21 to 28. What's that scale factor? It's 3 to 4, right? Or, of course, right, 3 to 4, or, and what we like with scale factor, and you guys have probably seen this for those of you guys who have done any sort of modeling. I don't mean you know, like having your picture taken. What I mean by that, like I'm looking actually right now as I do this live stream. My son had done a model, a scale model, that not perfectly to scale, but he's done a model of the Titanic. He's built a replica with Legos of the Titanic. It's actually pretty impressive. And some of you guys have seen these things. I mean, he's really into you know, the like Star Wars Legos, right? So the Millennium Falcon and what have you. So some of you guys though may be into model cars or may have had some of those, especially when you're younger. And what they'll have usually on the side of the box, right, is they'll have it in terms of 1, 2, and in this case, it's going to be, you're going to divide both of these guys by the initial thing, the initial number, right, to get 1. So 3 divided by 3 is 1, and 4 divided by 3 is 1 1/3 or 1.3 repeating. The reason that we like that mathematically is it gives us a single multiplier here that if you were to take the original, you can just multiply that up and it's that many times bigger for every single piece of the model or any single linear measurement that we have. For example, so if we have a scale model for a car and it's something like 1 to 40. What that means is, like, for example, the length of the bumper, right, for the model, if I multiply it by 40, that's going to be what the length is in reality of the actual car. Also, the exact measurement I take of the wheel, right, the diameter of the wheel, that linear length multiplied by 40, it'll be the same for the real thing, and it's going to match up for every single corresponding part. But let's make it a little bit simpler. We're just dealing with triangles. We have 3 parts that are going to be corresponding, okay? And again, as I just mentioned, all sides have the same ratio when similar. It's this, BC, right? That was this guy right here, second and third letters. BC corresponds to KL. BC is 36. KL is 48. Guess what that reduces to? 3 to 4, right? Or we already did AC. We need to do AB, which is going to correspond to JK, or 27 to 36, right? Which of course reduces, divide both by 9, and we get 3 to 4, right? When we reduce it. So all of those will have the same scale factor, but then we go back and they will have congruent angle measurements that are corresponding. So let's do a problem, like what we're going to see in our work. Let's see here. Draw out kind of a fun diagram here. Oops. All right, so let's label this guy. Looks like 2 triangles. I'm going to share at vertex H. Okay. And here are some dimensions. Oops. If we have a triangle GHM and it's similar to triangle HKL, then we're going to find X. Okay. So here's how we're going to go about that. We need to find this guy, X, which is KL. Now, guys, look at this. KL, second and third. So guess what? We're going to go to the second and third letters right there, HM. All right. Now we need to just set up another corresponding ratio where we have lengths that are given here. So let's just use this one, HL, right? That's first and third. That's 27. To GM, right? That's the other first and third. And that's going to be 18. But let me go ahead and make sure I set up the similarity statement first, or this proportion. Now we're going to go in and input the values that are here, right? KL is X. HM is 12. Right? HL is 27. And GM is 18. And then I get a solve for X, which, gentlemen, this is pretty straightforward, right? Just going to take a cross product here. And have 18x is going to be equal to 12 times 27, which if you punch that into your calculator, you got 324. And I divide both sides by 18, and x is equal to 18. So that is the value for KL. But it asks us to find x, right, which was KL in the first place. We just substituted x in there. Next, a couple more examples. Let's see here. Let's get a better triangle, guys. We can do better. Software can do better for us. In fact, I want to make this guy like kind of a little bit more scaling looking. That's fine. I don't like that one. Because I want to make sure that I have this guy's 36 and this guy's 36. So I want them to appear at least congruent, right? I have S, Q, T, and R. So, in the diagram, we have triangle U, V, W, and that's going to be similar to triangle Q, R, S, which means we're going to find the length of the median, ST, right? Remember discussing medians here, right? That median goes from a vertex to the midpoint of a side opposite, right? We learned that in the first semester. So now here's what you guys are looking at. And you're like, wait, I have QRS. Well, where's UVW? So let me give you the other piece of the diagram that I didn't draw out yet. Okay. Let's make this guy, he's going to be smaller. Oh my gosh, guys, I'm struggling here. There we go. All right. Similar deal, right? 16, 16 for U, V, W. And then this segment right here, or this is going to be segment Z, or point Z to give us the segment WZ. That's the median. The length, that median is 12. And as it turns out, every single portion of this, even these lines, perpendicular bisectors, altitudes, and medians, we're going to share in the same proportionality that each of the sides have. It's pretty straightforward. So in this case, WZ, right, which is the median, is going to be proportional to the other median, which is ST. All right? So median and median. Also, I want to show you guys another way to set up this proportion just when we get there. UV, right, which is that entire segment, winds up being proportional to the entire other lower segment QR, okay? Now, I'm going to show you guys something. What if I went like this? Let's just stay exclusive to this triangle. Let's say that we said median, WZ, right? To its bottom segment, which is UV, which is how some people like to set these things up, and that me included, right? Is going to be median, right? Medium to bottom given segment, right? Which is QR. That's the bisected segment. Well, look what happens when you take a cross product, guys. Isn't QR times WZ the same as WZ times QR? That's going to happen anyway. So it winds up showing that we can set up these ratios in this manner. At this point, I'm just going to be plugging and playing here so I can find ST. So I have WZ. I need to solve for that. ST over UV, which is, where is UV? It's 32 over QR, which is 72, right? 36 plus 36. And I'm going to take my cross product, right? So I'm going to have my 12 times 72, which according to my calculator is 864. All right, that's my cross product. And then another cross product, ST and 32 is going to be 32 times ST. Divide both sides by 32 to get ST by itself, which is going to be 27. Okay, so similarly, another little problem. Talked, of course, about my neighbors. My neighbor Lloyd, may he rest in peace, has been discussed before. Wonderful, was a wonderful man. Some of you may have neighbors who have gardens. Okay, so you're going to talk about your neighbor's garden. Because you like peek over the fence to see like how nice their yard is or not, right? Everybody's a little bit different. Like in that spectrum, I fall kind of in the middle. Not the nicest of the yards, but surely not the worst. So your neighbor has decided to enlarge his garden. The garden is rectangular with sides of width 6 feet and length 15 feet. The new garden will be similar, the keyword there, to the original. It will have a side length of 35 feet. Find the perimeter of the original and new garden. So, fun stuff. Here we go. Perimeter. How do we do that? Well, let's go back here. 15, 6, right? Remember how we find perimeter, especially if it's a rectangular garden, which is what we're going to assume here, is 2 times the width, which is 6, right? It's a rectangle, so we have 2 matching sides opposite each other, times 2 times the length, right? Perfect. It's 42, okay? But here's how we're going to figure this out. Now look at this. This is your perimeter, okay? So we need to find the perimeter of the original new garden. Now we don't have the length of it, but it doesn't really matter, right? Because what we're going to say here is, okay, well, we have a side length of 35. So that's my L, okay? So let's figure out my scale factor here. My length was 15 feet before, right? So length and length, the length 15 to the other length 35 will be a scale factor of 3 to 7. Now, what we need to know here is the following fun factoid, which is that the perimeters also, because it's linear, have the same ratio. Not ration, ratio. Okay? So we're just going to go old to new, right? Which is 3 to 7, which is equal to the perimeter, which is going to be 42, to the new perimeter, which is P, right? And then we just solve from there. We're going to do a little cross product, right? So we have 3 times P is equal to 7 times 42, which is 294. It's 294 divisible by 3. Sure is. 2 plus 9 plus 4 is 15. So it goes in, and X is equal to 98. Or P, sorry, capital P. What does that mean? This is the perimeter of the new garden. All right. Last thing for today, for this lesson. Oh, thanks for hanging in here. And it has to do with the following. If we were going to take proportional polygons, right, or excuse me, similar polygons, which are proportional, here's how it works when we are dealing with non-linear lengths. In other words, when we're dealing with area, for example. So we're going to take KLMN, which is going to be a quadrilateral, right, because there's 4 vertices that are identified, similar to PQRS. Okay, if this is the case, which it is, then the areas are going to be proportional in the following way. The area, I'm sorry, I'm really struggling to write the word area legibly for you. Area KLMN to the area of PQRS is going to be the overall. Remember how you find area, it's going to be a length times a width, and it's done in square units. So we have to go with the linear side lengths that are corresponding to each other squared, right? So KL, right, which corresponds to PQ, would have to be a squared ratio, okay? So let's set those all up. They're all going to be, right, equal to each other. So LM, right, so the top, right, top to bottom or first to second. So LM, second and third letters to QR, but of course that's going to be squared. We have MN to RS squared, and of course we have KN to PS, right? Squared, right? It's got to be this guy to this guy. First statement to second statement, right? Or top to the bottom. So let me draw it out for you. Ready? Looks kind of like a little trapezoid here. All right, we draw that guy up. We have, here we go, K, L, M, N, P, Q, R, S. We have 2 lengths here. We have this length of 7 and PS is 21, right? So there's these corresponding parts here. And then the area of KLMN is 48 meters squared. And for PQRS, the area we don't know. So let's find that area. How do we do it? Well, area to area, right? Left to right. So we're going to say KLMN is 84. To the other area we don't know, X. And then now we're going to say to their corresponding linear parts, right? So 84 is the one on the left. So I'm going to take the corresponding linear length given 7, which corresponds first 2 letters to, first and fourth is going to be first and fourth PS, which is going to be 21. But again, it's going to be that quantity squared. So this is how we're going to go forward and solve this. Here's where, of course, you need that calculator, right? Because you're not going to do this. You're not going to do 7 and squared. Of course, that one you're going to do, but 21 squared? Come on. That one's going to be 441, right? Of course. And then, you get your cross product then. So 441 times 84 is 37,044. This is light work for a calculator, right? So for those of you guys who are sitting here taking notes and, for some reason are doing mathematics without a calculator available, you know, because it's just like, oh, well, my phone's a calculator. But of course, you don't have access to that when you're doing like real mathematics, you know, especially on a test. So might as well continue the habit of having your calculator always available. Divide both sides by 49, and we're going to get an x, which is 756. What does that mean? It means the area is 756 meters squared. Okay, so that's it. That's the lesson 8.1. If you have questions, please feel free to reach out via email or Canvas, or see me during office hours.